Now we are going to start with the lecture number 2 of the classical mechanics, that is associated with the Newtonian mechanics first of all. And in this we have to discuss for the frame of reference, which is very necessary for the relative motion to be observed um, in the um, in the case of Newtonian mechanics or the Galilean frame of reference. That is you are going to study for the semester of your BS 5th, and the course code for your subject is PHY 509. Now we have to start with the Newtonian mechanics. We have discussed before about the Galilean and the Newtonian mechanics and the different definitions arising from the mechanics, that we study the motion of the objects and not the cause in the mechanics. So uh, previous introduction is in your mind. Now we have to start further for the classical mechanics. Uh, According to the Galileo, that there must be a force for the change in the rest or motion, and this was again formed or discussed by Newton's law, and that is said that Newton's law said that these rules were discussed as the law, and he said that according to Newton's law given by the rule from the Galileo, he stated three laws: Newton's first law, second law, third law. And from the first law, the state of rest or motion should be remain in the rest or motion, even till then no external force is applied on it. So frame of references are also associated with this, and classical mechanics is a very much associated with the discussion of the frame of reference, and frame of reference with the two types of frame of reference, that is inertial and non-inertial frame of reference. In this lecture we will discuss about the and definitions for the frame of reference, and um, different types of examples will be shared here to understand what is frame of reference, and at what time the inertial frame of reference will be converted into non-inertial frame of reference, at what time will be non-inertial frame will be converted into inertial frame of reference. The following are the contents we have to discuss in the frame of reference. First of all, we have the definition of that what is frame of reference. Then we have the definition for the inertial frame of reference and some examples. Further, we have non-inertial frame of references and its examples. Then there is a difference between the two frames, and with examples we will discuss what is the difference between two frames. And in the last, there are some references of the topic from which you can have some guidance. Now we will start with the frame of reference. Now we will start. What is the frame of reference? A frame of reference is a coordinate system relative to which the position of motion of an object may be described. To find the position of an object, we can use frame of reference. Is it possible? It means that to define a form of frame of reference relative to which the motion of the object is to be described. Is it possible that the position of the object can be found by the frame of reference? For the answer of this question, we will consider an example. First of all, we will consider example number 1, in which we are taking a bus which is moving with a uniform velocity with 30 kilometer per hour along a straight line on a road. An observer A. Now we will consider that an observer A is sitting inside the bus and another observer B is standing outside the bus on the road at rest. Now imagine a dog is running inside the bus with a speed of 5 km per hour. Now what will you refer with both observers? First observer is inside the bus which is moving with 30 km per hour, and inside the bus at the same time the dog is moving with 5 km per hour, and another observer is standing outside the bus on the stationary road. Then what will be the speed of the uh, dog with respect to the observer A and B? For observer A, dog velocity is 5 km per hour because the dog is inside the bus with the observer in the bus, and the both bus and the dog are moving. It means that the frame of reference regarding the observer A is the bus to observe the motion of the dog. In the another case, when the observer is standing outside the bus on the road, he is the bus in the motion and the dog in the motion as well. You know that the bus is moving with 30 km per hour and the dog is moving with the velocity 35 km per hour, and the observer outside the bus on the road is at rest. It means according to his frame, the both think he is in the rest and he is observing the frame of reference which is in motion, and the objects both are in motion. So the velocity of the dog appears to him as 35 km per hour. Now we will consider another example to understand what is a frame of reference. Now we'll take another example. Here is another example too. Consider a train moving in a straight line. If person throws a ball upwards, its trajectory will be a vertical line. Now we are taking a train that is moving along a straight line, and in the train, if a person throws the ball upward, the trajectory of the ball will be a straight vertical line, but the observer on the platform will not observe the trajectory as a straight line, but he observes the parabolic path. It means that both the frames are different from each other, and the observation of the observer from in the train and outside outside the train on the platform, there are two observations, so there are the two different trajectories observed. Now here both rest frame and moving frame are relative to each other. We have discussed that rest and motion are relative to each other. So it means that if one frame is at rest, the other can be in rest or in moving, or both the frames can be in motion, or both can be at rest. It depends upon the reference or the relativity of the both frames to observe the different kinds of motions of the same object. As I have told you before that the first statement of Newton's first law, the term state of motion is used. The state of motion is a relative quantity. I have told you that the two states, either of rest or motion, are relative to each other, but that depends that which of the observer is going to observe from which state or the frame. So to observe the motion of the object, we have to have a frame of reference. So the question here is that the object being observed is at rest or in motion with respect to which observer. So in this, the observer plays a main role for the uh, study or of the object, whether it is at rest or in motion. Since state of motion is a relative quantity, so we must take into account the frame of reference in discussing the Newton's law of motion. We can say that the frame of reference is a laboratory or a place where we observe some phenomena and take measurements. That we can say that frame of reference is a place or a area in a kind of lab where the measurements are observed and phenomena is observed. Then depending upon this, we can say that the frame of reference is of two types. The first is inertial frame of reference and non-inertial. Second is the non-inertial frame of reference. You have studied about the inertial frame of reference and non-inertial frame of reference with some simple definition. That inertial frame of reference is that in which all the Newton's laws are applicable, and non-inertial frame of reference is that in which Newton's laws are not applicable. So further we have to differentiate and by some examples that what is inertial frame of reference and what is non-inertial frame of reference. Now we are going to take the space-time coordinate. It means that to define a frame in rest or motion, we should have a coordinate system. The space-time coordinate system means that the three axes of xyz with the time coordinate fourth axis should be there. So for the frame, we can say in a moving frame, time has to be measured on a definite scale. It means that if the frame is moving, then we should need a definite time for the observation of the motion. So there should be a definite scale, and is required to know the position of the particle with reference to the time. Then we must assign one more coordinate with x, y, z, and that is time t. Such a frame of reference will be called reference frame will be called space-time coordinate, and it will have four coordinates x, y, z, and t. Here you can see that there are four coordinates x, y, z, and t that define the space coordinate system, and that is used for the formation of inertial frame of reference regarding with the frame in motion. Now, according to the frame of reference definition and with the space-time coordinate definition, we can say that there are two types of frame of references. The first one is the inertial frame of reference, and second is the non-inertial frame of reference. As there are two types of inertial frame of reference we discussed, the first kind is inertial frame of reference. The frame that obeys Newton's law of motion is called inertial frame of reference. You know the definition for the Newton's law, that is the object in rest will remain in rest and the object in motion will remain in motion unless unless if an external force is applied on it to change its position or direction. Also, that inertial frame of reference is called Galilean or Newtonian frame of reference regarding to the Newton's law. In the definition, I have told you that Galileo gave some rules for the motion of the object. So that rules were then worked out by Newton, and the laws were called the Newton's law. So in Newtonian frame, that frame, inertial frame, is also called the Newtonian frame or the Galilean frame. And you know that the two frames are relative to each other, and you know that in Newton's law, F is equal to ma means force is directly proportional to acceleration and mass is proportional to acceleration is inversely proportional to mass. Now, if the force applied on the body F is equal to 0, then the acceleration produced by the body is 0, but mass is not equal to 0. As we have taken the Newton's law of is equal to ma, if force is not applied on the body, then there will be no acceleration, but the mass will be present there. You can take an example of the car. If it is in rest, you can say that there is no external force applied on the car to stop it or move it. Then the car is at rest, so acceleration is 0, but the mass of the car is not 0. Now, as inertia, we are dealing with the inertial frame of reference. Then inertia is a property of matter that we have studied in many times in previous classes as well. It is the property of the matter which opposes the change in the velocity. So inertial frame of reference is associated with the property of the matter, and that is the property of the matter that opposes the change in the velocity. So one must center one's physics on these thoughts, that the inertial frame of reference can be regarded as an object's velocity will not change all in or on its own. Pushes or pulls are necessary to change the object's velocity. It means that there must be some kind of push or pull for the velocity to be get changed. So inertial frame of reference is associated with it. So regarding this, we can say that there are several ways to describe an inertial frame. Here are few descriptions. Number one, an inertial frame of reference is a frame of reference with constant velocity. And number two, an inertial frame of reference is a non-accelerating frame of reference, as it is associated with the Newtonian's law, and according to the Newton's first law, the state of rest or motion should be remained as it is till then any external force applied. So according to the inertial frame of reference, there should be the constant velocity of the frame, and the inertial frame uh, is should be a non-accelerating frame. Now at number 3, an inertial frame of reference is a frame of reference in which the law of inertia holds. At number 4, an inertial frame of reference is a frame of reference in which Newton's law of motion hold, that we are discussing overall in the topic of the inertial frame of reference and non-inertial frame of reference with their examples. At number 5, in an inertial frame of reference, no fictitious force arises. As we are going to discuss for the non-inertial frame of reference, there are some kind of fictitious forces that are also arises, and they are the associated with the non-inertial frame of reference. But inertial frame of reference, there is no any kind of fictitious force present. There are some kind of actual changes in the motion of the body in the inertial frame of reference. Now, is our if do we think that an earth is an inertial frame of reference? For this, you can see that earth is revolving around the sun and continuously in the motion with the change in its velocity. It means that the earth is continuously revolving around the sun, and it means that with velocity acceleration is being produced. So earth has both rotational and revolutional speed. It means that the earth revolves around the sun, that is rotation, and the revolution means that it revolutes or spins in its own axis, but its speed is very less. The centripetal acceleration for it is 34 centimeter per second square, that which is very small in amount for the to be observed by the objects on the earth, so we can say that is negligible. Now we take an example. If we toss a coin, it comes back in a vertical, it will not take a parabolic path. So earth is an inertial frame of reference. It means that uh, the frame is the same, and the observation of the object is same, so that is the inertial frame of reference. Otherwise it is very difficult to calculate other values. It means that if the earth is not inertial frame of reference, then to calculate different other values will be quite difficult to calculate, because at instance inertial converts to non-inertial frame and non-inertial converts to inertial frame, that at certain times. So under the earth reference, the frame will be inertial. Now the second type of frame of reference is non-inertial frame of reference. For this we can state that a frame of reference which does not obey Newton's law of motion is called non-inertial frame of reference. Non-inertial means the frame of reference which doesn't move with the uniform velocity. It means that at certain time it has a one kind of velocity, and at the other time its velocity is changed, that is called the non-inertial frame. And for this, the acceleration of the body is not equal to 0. It means that the if the force is 0, the acceleration is not 0, but it has different values. For applied force on the body is 0, if the force applied on the body is 0 but acceleration is not 0, hence the frame is called accelerating frame. It means that if we apply a force on the body and the body does not move, it means that force is 0 but the acceleration is not 0. We can have an example for it in the further slide. I will explain it. So that frame, as acceleration is not 0, is called accelerating frame. Now there are some kind of acceleration non-inertial frame of references. Here are some examples. The first one you can see is any vehicle taking turn on the road. The other is the merry-go-round, the you can see in the second picture. And third one, the example is the sudden start or stop of the vehicle. It means that if you suddenly start, it stops, or it suddenly stops while driving. That is the example of the non-inertial frame of reference. And the moving of a lift in upward and downward direction is also the example for the non-inertial frame of reference, in which accelerations are not 0 but force is 0. Now if the force F is equal to ma be acting on a particle in an inertial frame S, the force acting in reference frame S prime, then the force in S prime will be F prime is equal to ma minus ma naught. Here Newton's second law is not valid. Put F is equal to F naught is equal to minus ma naught and F is equal to ma. Then minus F prime is equal to F plus F naught. If F is equal to 0, then F prime will be equal to F naught and that will be equal to minus ma naught. That is the example for to state that when the frame is non-inertial and the acceleration is not 0. Now another example for the non-inertial frame is a pseudo force, a force which doesn't act on the particle directly and the force actually doesn't exist but appears to come in consequence of the acceleration of frame S prime with respect to the S. This force is called the pseudo force or fictitious force. It means that we can say that pseudo force is a fictitious force that we uh, feel at some time suddenly on the motion of the object. For example, if we are driving a car and suddenly we apply brakes, we feel that some kind of force is being applied on us. That is a pseudo force. That is actually not a force but a fictitious force or non-actual force applied on the body. The another example of the we can say is of the lift. We are standing in the lift and we see that feel that that when the lift is going upward or downward, we feel some kind of force that is acting on our body on the above side or below side, but that force is actually not being applied on us. That is the feeling force. We feel that is the pseudo force. We can have an example here, the pseudo force. So I can say that here are two examples. Do you feel like someone is pushing you backwards when a car accelerates forward? Here you can see the two examples. You can see the example of a car in which you can see a person is driving, and here you can see the car is accelerating forward and the person is feeling that there is some kind of force feeling on him in backward direction, but actually there is no force being applied on him. So there we can say that is a pseudo force, a fictitious force. And another example is of a elevator. A person is standing in the elevator and the elevator is accelerating upwards, and there is some kind of force felt on the body of the person in the downward direction. Actually there is no force being applied on it, but there is a some kind of fictitious force felt on the body, that is called the pseudo force or the fictitious force. Another example for the non-inertial frame of reference is the Crowley's force. In case of rotational frame of reference, pseudo force is known as Crowley's force. When the frame of reference is a rotational frame of reference, then the pseudo force acts as a Crowley's force because it is in rotational form. This is observed acceleration in the rotating frame. That is observed. You can say that in the Earth rotational motion, an apparent force that arises because of the Earth's spin around its axis. Freely moving objects are deflected to right to their direction of motion in the northern hemisphere and to the left of their rotation of the motion in the southern hemisphere. And on equators, that Crowley's force is absent, and that Crowley's force tend to keep the object on their place where they are at actual. So that is also a fictitious force but in the rotational frame of reference. Here you can see that there is an example for the earth. Upper one is the northern hemisphere, below is the southern hemisphere, and the earth is rotating. The objects of the northern hemisphere tend to move in the right direction, and the southern hemisphere, the objects tend to move uh, in the opposite direction. So we can say that what is the Crowley's effect? The rotation of the Earth causes all the moving objects in the northern hemisphere, including the air mass, to deflect to the right, and those in the southern hemisphere to move in the left. This Crowley's effect is absent at the equator. Crowley's force prevents a direct, simple flow from the equator to the poles. This is known as the Farrell's law, Crowley's force directly prevents the flow of the objects from the equator to the poles. That is called not called the Crowley's force, but that Crowley's force is called the Farrell's law. Here are some examples for the Crowley's force, that are the tidal force. You can see the example and a picture that how the tides are formed in the sea waves, sea water. Another is the example of the cyclone. Cyclones mean the motion of the wind or the water in the circular shape. And another example is the of the a fly walking on a rotating fan. You can see on the third picture. These are the examples for the Crowley's force, which are in the rotating frame. You can see these are the examples for the Crowley's force, that are also the Crowley pseudo forces, but their frame is in the rotating frame. Now further we will discuss, starting with the inertial and non-inertial frame of reference. First of all, recall first law of motion, that is law of inertia. We have discussed earlier that the first law of motion of Newton's law is also called the law of inertia, and I told you that inertia is the quantitative measure of a mass. So an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. You know that for the object to have some motion or change in motion, there must be an external force applied by some source, which I have told you that Aristotle said that there's a Aristotle and Galileo said that there must be some external force for an object to be in motion, or its direction of motion should be changed. I have given some examples previously. The example of a ball hit by the bat, a person pulling a box with some force, and the fall of an apple with the gravitational force. All these kinds of atoms show examples show that the state is changed when the external force is applied, and it means that the inertia will remain as it is when there is no external force, whether it is in motion or whether it is in rest state. We have already talked about frame of reference in this course, uh, starting from the course. When we talked about relative velocity, you know that a person sitting on a bus watching a ball roll across the ground will have a very different measurement of the ball's velocity than a person standing outside the bus would measure the ball's velocity. If we consider a ball that is in the bus, and there are two kinds of frame of reference. The bus is in motion. The frame of reference with respect to that ball, this frame of reference, the bus is in motion, and the other frame of reference is outside the bus, and that is the another frame of reference. But the observer standing outside the bus will observe two kinds of frame. One is in motion, and according to him, which he is standing in, that is surrounding as a frame of reference, that is in rest. So the velocity depending upon these two frame of references will be different. The We can say that if the frame of reference and the object are uh, same in motion, then the velocity will be same for this object, but for the person standing outside the that frame which is in motion, he will observe the velocity difference between the two frames of his and the bus. So the velocity of the ball will be lesser than the actual velocity observed in the frame of reference of the bus. Here is an example which is of bus. You can see that the person is standing in the bus, and the bus is moving with the speed of 20 km per hour, and the ball is moving with the velocity of 5 km per hour, and the observer standing outside feels the difference between the velocity of the ball, and he observes or she observes that velocity is 15 km per hour. because the ball is in the and in that frame which is also moving and the object is also moving, but the observer standing outside the uh, frame feels to observe that the velocity is 15 km/h. That is the difference between the velocity. The person inside the bus and the person outside the bus are measuring from different frame of references. Let's change things a little. Imagine that you are traveling on the bus with a ball inside you, sitting on the floor. The bus is moving forward at a constant velocity of 20 km/h. You can see the example as the bus is moving with 20 km/h. Move, which is as it should be because there is no net force acting on it. The ball should not move on the floor because there is no external force acting on the ball. According to Newton's first law, it should remain in rest unless there is an external force applied on it. But you can see that the person standing inside is also observing that the ball is at rest and the frame that bus is moving with the 20 km/h. But you can see the person or any other thing is not placing any kind of force on the ball. So so when suddenly the brakes are applied on the bus starts to deaccelerate, and you can see the motion of the bus is slowing down. So you see that the ball is suddenly in motion in the opposite direction. Can you observe that is there any force being applied on the ball? Actually, there is no force being applied on the ball. Suddenly the bus starts to deaccelerate and the ball starts to accelerate towards the front of the bus. You can see that from the red arrowhead on the ball. The observer inside the bus observes that the ball suddenly moves towards the front side of the bus. Is there any force applied on the force actually on the ball? You can see there is no actually applied force on the ball there, but you can see that the acceleration provided some kind of force for the object which was in rest, and according to Newton's law the ball should remain in the state of rest during that state. But if there is no external force applied, you can actually see there is no external force applied on it. But when the bus is being slowing down, there is a force applied on the ball which is not observable, but the ball is observable due to its motion towards the front side of the ball. Due to inertia, it tends to move in the front side of the bus. Since there is no net force acting on the ball, means that no one pushed it. What is going on? Does this violate the Newton's first law? First law means that what is Newton's first law? Newton's first law is that the state of the object should remain as it is till then there is no external force applied on it. The observer also observes that are the laws of the physics deteriorating, means that are they being violating? What do you think, that are these laws being violated here when the bus is slowed down and suddenly the ball started to move towards the front side of the bus? What do you think? We can say here the laws of physics seem to momentarily break down for you sitting on the bus. If you are sitting on the bus and for the sudden moment when the deceleration is provided, then you see that at a sudden moment the laws of physics are violated or disturbed or break. In reality, what has happened is that your frame of reference has been compromised. Means that in which frame of reference you are being observed or observing that object, that is being comprised for a certain moment of time. An inertial frame of reference is a frame of reference in which the law of inertia and the other physics laws are valid. It means that if that frame of reference is a inertial frame of references, then the laws of physics and the law of inertia should be valid here. There should not be any difference here, and the state of rest or motion should be the same as it is. then any frame moving at a constant velocity relative to another frame is also an inertial frame of reference. If the one frame in which all the inertial frame of inertial and law of inertia and the physics laws are applicable, then any other frame from which are you observing that frame of reference should also be the inertial frame of reference. What happens? What happens here? You see that when the brakes are applied to the bus undergoes a negative acceleration. What is negative acceleration? It means that when the bus applies some brakes, then the speed of the velocity starts to slow down, and that causes a negative acceleration. At this moment, when the deceleration started, that moment it becomes a non-inertial frame of reference, as previously said that when the brakes are applied at certain moment of time, the frame of reference has been compromised. It means that at that moment, when the constant acceleration converted into deceleration due to applying brakes, that inertial frame of reference suddenly shifted to a non-inertial frame of reference. And a non-inertial frame of reference is a reference frame in which the law of inertia does not hold. It means that at that moment, the law of inertia wasn't valid, and the object wasn't in the same state as at rest, which you have observed earlier. So at that moment, the law of inertia wasn't applicable on that object when the frame of reference was non-inertial frame of reference. Although the ball accelerates towards the front of the bus, there is no net force causing the acceleration. It means that you have not observed any external force being applied on the object, the ball, to be said to be change its states of motion. But when you are sitting in the bus, you observe that the ball accelerated towards the front side of the bus in the forward direction. That would imply to you, as you sit in the bus, that there is a net forward force applied on the ball. Means that there should be some external force applied at that moment when the inertial frame of reference was compromised with a non-inertial frame of reference where the law of inertia does not hold. At that moment, the ball started to move due to its inertia towards the forward side of the bus. The reason there appears to be a net force on the ball is that you are observing the motion of the object in the non-inertial frame of reference. It means that the ball at that moment is moving due to the non-validity of the law of inertia, which is the main statement or main property or the rule for the Newton's first law to be applicable. Now, if you were observing the motion of the road, which is an inertial frame of reference, the ball just continues to move forward at the speed it was already going, but its motion is easily explained by the law of inertia. If you observe the road as an inertial frame of reference, then the ball should move forward at the speed with which it was already going. But by this motion, we can say that law of inertia is well explained. To an observer in the inertial frame of reference, the ground, the bus experienced a net force causing to deaccelerate. The bus felt deacceleration due to the ground, so the ball just continues its forward velocity with no net force. To explain the ball's motion, if you are sitting on the bus, you need to invent a force that acts on a ball towards the front of the bus. Means that if you are to set that you have to create an external force for the motion of the ball, there should be a force provided on the ball that should be a fictitious force, that is invented force that we can use to explain the observed motion in the accelerated frame of reference. Now, to understand the non-inertial frame of reference, we take an example. Here is the example number 1. You are on a train which is initially traveling at 12 meters per second in the east direction. You gently place a tennis ball beside your seat. Number A, you have to find what happens to the tennis ball in motion. Number second, B part, draw an free FBD, means free body diagram, of a ball in the frame of reference of the ground outside the train and the frame of reference of the train. And third thing is to find the train starts to accelerate at east. Draw a new free body diagram FBD of the ball in the both frames of the reference. First of all, you are in a train which is initially traveling with the speed of 12 meters per second in the east direction. You gently place the ball beside your seat and you have to find ABC part. What happens to the tennis ball motion? Draw an FBD of the ball in the frame of reference of the ground outside the train and the frame of reference of the train. Number C, the train start to accelerate east. Draw a new FBD of the ball in the both frame of references. Now for the first part A, the ball remains stationary relative to the bus because of the uh, set force among on it is zero. However, the ball moves at a constant velocity of 12 meters per second in east relative to the road, the same as the velocity of the bus relative to the road. For the B part, the FBD of the FBD is the same in each frame of the reference. You can see Fx is in downward direction, Fy is in F normal or is in upward direction of y. You can say, and the right hand side you can see that x direction of the axis and the y direction of the vertical direction. As the bus For the C part, as the bus accelerates forward relative to the road, the ball begins to roll backward relative to the bus experiencing the acceleration. Now we are taking a second example, example number 2. A rubber stopper of the mass 25 gram is suspended by the string from the handrail of a subway car traveling directly westward. As the subway train nears the station reaches the station, it begins to slow down, causing the stopper and the string to hang on an angle of 13 degrees from the vertical. We have to find in the A part what is the acceleration of the train, and in the B part determine the magnitude of the tension in the string. A rubber stopper of the mass 25 gram is suspended by string from the handrail of a subway car traveling directly westwards. As the subway train nears the station, it begins to slow down, causing the stopper and the string to hang at an angle of 13 degrees from the vertical. So the first part A, what is the acceleration of the train? Take m as m is equal to 25 gram. Mass is 25 gram, theta is 13 degrees. Number A, we have to find, consider the vertical component of force with positive y up. Summation Fy is equal to MAy is equal to 0. Then f tau cos theta minus mg is equal to 0. F tau cos theta is equal to fg, where fg is equal to weight is equal to mg and ft is equal to mg over cos theta. Substitute into the equation from the horizontal components with the positive x east. Summation fx is equal to is equal to max. Ft sin theta is equal to max and theta is equal to ft into sin theta over m. That gives mg over cos theta into sin theta over m, and g is equal to sin theta over cos theta. That gives g into tan theta as sin theta over cos theta is equal to tan theta. G value is 9.8 meter per second and tan theta here will be tan 13 degrees, and here a theta t will be equal to 2.3 is equal to 2.3 meter per second square. That is not theta t. That is the acceleration. Ax is equal to 2.3 meter per second, and we are calculating for the acceleration of the train. So Ax is equal to 2.3 meter per second square. Thus the acceleration for the train is 2.3 meter per second square in the east direction. A rubber stopper of mass 25 gram is suspended by the string from the handrail of a subway car traveling directly towards westward. As the subway train nears the station, it begins to slow down, causing the stopper and the string to hang at an angle of 13 degrees from the vertical. Now we have to find the B part. Determine the magnitude of the tension in the string. At B part, consider the word for the solution of the B part. We consider the vertical component of the force in the positive y direction. Summation Fy is equal to 0. F tau cos theta plus into minus mg is equal to 0. Then F tau is equal to mg over cos theta. Substituting the values for the mass 0.025 kg, we have converted 25 gram into kilogram. That will be 0.025 kilogram into g value 9.8 meter per second squared divided by cos 13 degree, and that after calculating F tau is equal to 0.25 Newton. Thus the magnitude of the tension in the string is 0.25 Newton. That is the solution of the B part. Previously calculated the acceleration for the A part of the train 2.3 meter per second in the east direction, and the B part is that. Are the two examples for the non-inertial frame of reference. Here is an example of a roller coaster. That what does this have to do with the roller coaster? How the inertial and non-inertial frame of references play a role in the roller coaster. One of the things that makes roller coaster fun is feeling of the weightlessness. You have when you are going down a big hill, you feel the weightlessness. That feeling of weightlessness occurs because your apparent weight as you are in the fall in the free fall down the hill is zero. It appears to you the actual weight of you is not zero, but the apparent weight means that the weight that appears to you feel is the apparent weight in the weightlessness that is felt zero. So we can say apparent weight is the magnitude of normal force acting on an object in a non-inertial frame of reference. Here you can see another example that when we are standing up on a level ground, we experience a normal force up. This is the force of the ground against our feet. If you stand on a bathroom scale, the normal force up is equal to the weight of the scale, that is mg, towards the down. Technically, we are speaking about the weight, that is W is equal to mg. You can see from that example on the right hand side, a scale does not measure your weight, but the scale measures the upward force applied by your body, which should be equal and opposite to the normal force applied by the ground. If if we are to put the scale in the elevator that is not in the ground, which is accelerating downward, then the normal force will decrease. What does that mean? That the condition is of weightlessness and your weight reading on the scale will appear to be less. And as the frame of reference of the elevator and the object of scale is moving with the same speed as the elevator, so the weight appear on the scale will be less. You haven't actually lost any mass, but in the accelerated frame reference, the normal force decreases because you and the elevator are accelerating. Then the normal force, which should be equal to the weight of the object, are not equal. So on the scale, we do not uh, observe the mass and we do not observe the weight as it is was observed being before. So it appears to be less or decreased, and therefore the weight will read on the scale will be lesser, which appeared greater before. Here is an example of the elevator. You can see the first picture there is an elevator with the acceleration 0. The person is standing on the scale with the in the rest state, and the object or the person has the weight W is equal to mg. You can see with the arrow at the downside. In the second picture, you can see the elevator is moving in upward direction. In that case, acceleration will be equal to the gravitational acceleration g, and the both the weight will act downward. W is equal to mg, so the weight will feel double the weight of before, then that will be W is equal to 2 mg. But if the elevator is falling downward, then the acceleration is equal to negative acceleration, means in the opposite direction. So the weight of the object W is equal to mg is downward, and the weight of the elevator or the floor of the elevator provides the normal force, which is lesser in amount in the upward direction, that is minus mg. That means that the weight of the object will be lesser and nearly equal to 0. We can say that is the condition of the weightlessness, W is equal to 0. The previous example of the elevator, we can see that the frame of reference in motion or in rest depending upon in which direction it is moving. The observer decides whether the weight of the object will how be affected. Now, when the elevator is being accelerated, the new weight in this accelerated in the non-inertial frame of reference is called the apparent weight that appears to you in that case. If you are sitting on a chair, then you feel a gravitational force downward and an equal and opposite force of normal in the upward direction, and you are in the state of rest. But if the person is sitting in the chair and is in a he is in a space and falling with the uh, gravitational force, then the weight appear to him is W is equal to 0, and we can say that the he feels no weight or the lesser weight, uh, W is equal to 0. On a roller coaster, when you are in the free fall down a large hill, the acceleration of the ride is equal to g is equal to 9.81 meter per second square, and the normal force between you and your seat becomes 0. This makes your apparent weight 0 as you go down the hill, and is the reason you feel the weightlessness. You no longer have the normal force of the seat pressing up you against the seat. So the only weight appear to you is your own weight, and the gravitational force being applied on you, and you feel that your weight is W is equal to 0. There are different examples in the daily life, as you can see that in the parks or in the dry land there are many kind of swings or fun areas in which you can say there is a condition of weightlessness. There is a kind of swing, or we can say that it's called discovery, in which you can feel your weightlessness when the gravitational force is only acting on the object, and the person sitting on the seat, there is no equal and opposite force applied by the ground on it. So the only force acting on the object is the gravitational force. There he can or she can feel the weightlessness, means that the weight appeared to him is equal to 0, and he or she can fall under the effect of the gravitational force. Before that, we will discuss some introduction or overview of the inertial frame of reference again. The frame of reference where Newton's law of motion are absolutely valid is called the inertial frame of reference. In other words, if a body is a subject to no external force, means not accelerated, then the frame of reference is called the inertial frame of reference. If the Newton's laws are valid in one inertial frame of reference, then they are valid to in any inertial frame. A valid reference frame may be Earth or distant galaxies. It depends upon the situation of our problem, that what kind of frame we should have for their discussion. And the non-inertial frame of reference, the frame of reference where Newton's laws of motion are invalid, is called non-inertial frame of reference. In theory of relativity, we see that there is no body at absolute rest or in absolute motion. It means that the state of rest is not absolute and state of motion is not absolute. There must be some external force present to make the natural frame to the non-natural frame. For instance, we at Earth are at rest at a given time, but if someone outside the Earth on another planet observes the Earth, it is changing its position all the time. Here we are at rest in the our frame, but we are accelerating in another frame. Thus, there is no reference frame which is absolute at rest or in motion. We can say in curved space time, all frames are non-inertial frame of reference. So here are some references of the books you can follow. First one is of the Goldstein, and the other I followed is the analytical mechanics, and the third one is classical dynamics of the particles and the systems and classical mechanics. And these are the reference you can take from the books. And if there is any kind of question regarding the inertial frame of reference or in a non-inertial frame of reference, you can ask me. Thank you.